So before talking about Kb, which is the base dissociation constant, I want to briefly talk about something that we've touched on a little bit, but I think it would help to talk about it in a little bit more in depth. All right, and that is that the fact that the terms HA and A minus are relative to each other. All right, so one thing that can be a little bit confusing is that if you see HA, you might assume that that has to be something with exactly one hydrogen and it has to be neutral. All right, and that you would assume possibly that A minus has to have 0 hydrogens and then it's got a -1 charge. All right, the thing is, these guys are only meant to be relative to each other. All right, and what that means is that the only thing that's true is that A minus is what you have after your HA loses an H plus. All right, so the thing that's always going to be true is that HA has one more hydrogen and one higher charge than A minus. All right, and so I think that it helps to see some examples for that to make sense. All right, so if I were to show this particular acid dissociation, all right, and this is just shown in the Arrhenius form. All right, so we've got H3PO4 yielding H2PO4 minus plus H plus. All right, so in this particular reaction, this would be your HA and this would be your A minus. All right, notice that your HA is actually something that's got 3 hydrogens. All right, and that your A minus has 2 hydrogens, even though generically you're saying A minus, which doesn't have any. All right, the thing that's important here is that this thing right here has got one more hydrogen than this. All right, also it has one higher charge, it's neutral, than this right here. So a 0 charge is one higher than a -1. All right, so for this particular reaction, we could describe or define a Ka, all right, where this would be your A minus and this would be your HA. All right, so this particular dissociation would have its own Ka value. All right, so what I'm going to do here is I'm going to take this guy, and one thing about this is it also has the potential to act as an acid. All right, so I'm going to show that acid reaction right here. So if this guy right here were to lose one of these hydrogens, all right, it would become this guy right here, and here's the H plus that it lost. All right, so notice in this particular reaction, this would be your HA. So notice what your HA is in this reaction is actually what your A minus was in this reaction over here. The important thing is that it's relative. You have both an HA and an A minus in this particular reaction. All right, so in this reaction, this is now your A minus. All right, and again, same thing. One more hydrogen over here and one higher charge. All right, so this particular dissociation would have its own Ka, all right, where this is your, this would be your A minus, your HA is in the bottom. So notice that, and again, we're doing the same thing right here. So the one thing I want to point out is that the numeric value of these 3 different Kas would all be different, all right. So this particular dissociation reaction right here is it's going to have its own Ka value, all right, which is going to correspond to this. This one is going to have a totally different Ka value. All right, so just because I wrote them both as Ka does not mean that they're the same number. All right, so they would actually be different Kas. So one other thing that I wanted to show is that HA and A minus can also be used to describe a base. All right, so this is just, from this is a standard Bronsted-Lowry reaction. All right, and if I were to say, let's take a look at this guy and this guy right here. All right, and if I were to say, what is this guy right here acting as? Well, you could say, well, it is going from here, to over here, it is accepting an H plus. So therefore, it is acting as a base. All right, so you might say, well, we haven't come up with generic terms to describe a base. All right, well, let's just think about this. All right, this guy has got one higher charge. Sorry, this guy right here has got one higher charge than this right here. This guy right here has also got one more hydrogen than this right here. So we could refer to this, which we would commonly refer to as the conjugate acid of this base. We could call this HA, and we could call this A minus. All right, and again, you literally, even though your A minus is generically A minus, it doesn't literally mean that it's got a minus charge. It just means relative to the thing that has the hydrogen that would be true. So moving on to the concept of a KB. All right, so just like with weak acids, we could come up with this term called a Ka, which was a way of describing how well the conjugate acid donated a hydrogen. All right, so well, what bases do? Bases like to accept H pluses. All right, so we could come up with a generic base reaction, just like we had a generic acid reaction. All right, so for a generic, the generic base reaction that we're going to show is we're going to show A minus as being your base. All right, and we're going to have H2O right here, and it's going to give, once this base accepts NH plus, it's going to become HA, and that's going to also generate an OH minus. All right, so that's what's left over after your water donates a hydrogen. Okay, so I just want to point out that even though we've shown it like this, you'll sometimes see this shown where it's what they'll use for the base is to just use a capital B, all right, and then this right here would be BH plus, all right. So that's just another way of showing these two things relative to each other, but it doesn't change in the end the meaning of what these things mean. All right, so what a KB represents is just like before, we're going to show the things on the right side of the reaction in the numerator, and we're going to show one of the things in the denominator. All right, and again, remember in the Ka we did not show water, the concentration of water in the denominator, because it was essentially the concentration of water stays constant throughout the reaction. All right, because there's so much more water. All right, so for the same reason we don't include water in the denominator here. All right, so this is what the Kb would represent. All right, and again, if you're reading this from another textbook, instead of seeing HA, you might see this as BH plus. All right, so again, this thing right here would just have one higher charge and one more hydrogen than the thing over here, whereas the thing on the bottom would be just B. All right, an uppercase B. So again, we can get a sense of what it means about this reaction by the size of this term. All right, so let's assume that a base had a large Kb. All right, what would that mean? All right, so what that would mean if a base had a large Kb, that means you're going to have a high numerator and a small denominator. That means you're going to have lots of this stuff right here and relatively little of this stuff over here. All right, so what that means, in order for that to happen, that means that your base had to accept a lot of H pluses from water, all right, in order to make this, all right. So what that means is that that would be a relatively stronger weak base because it's doing a lot of what bases do. It's accepting hydrogen, sorry, it's accepting H pluses, all right. So by comparison, if something's got a small Kb, all right, that would mean not a lot of numerator and a relatively large denominator. That means not a lot of this stuff over here and lots of this stuff over here. All right, and the way that happens is that when your base comes in contact with water, it tends not to want to accept H pluses from it. All right, so if it doesn't tend to want to accept H pluses from it, then it's going to be a relatively weak base. All right, it's not going to be doing what bases do. All right, so a small Kb is going to indicate a weak base. All right, and so hopefully this is becoming familiar. Whenever we have a constant, we can put a lowercase p in front of it, and that means take the negative log of it. And what that does is it makes the number a little bit easier to deal with. All right, when you're talking about Kas and Kbs, you're talking about something in scientific notation. But when you're talking about pKas and pKbs, you're talking about a number that goes between 0 and 14. All right, so just like before, there was this inverse trend. So a large pKb, all right, is going to be a weaker base because a large pKb is going to come from a smaller Kb, all right, and a smaller pKb is going to correspond to a larger Kb. That's going to indicate a stronger base. So just like we had a relationship between pH and pOH, there's going to be a relationship between the Ka of an acid and the Kb of its conjugate base. All right. So please note that when I'm saying that talking about this relationship, I'm not talking about the Ka of an acid and the Kb of the exact same acid. I'm talking about the Kb of the acid's conjugate base. All right. So let me show an example of that. So if I were to show an acid, all right, I could show it with the generic acid dissociation reaction like this. All right. But notice that when that acid does what it does, it generates this conjugate base. All right. Well, that exact conjugate base has the potential of, by definition, acting as a conjugate base. And what bases do is that they can accept H pluses from things. All right, so we could show this acting as a base in this own separate reaction right here. All right, where the A minus accepts an H plus from water and generates HA. All right, so notice what we're going to be doing is we're going to be comparing the Ka of this acid right here to the Kb of its conjugate base. All right, remember A minus and this A minus are the same thing. That was the conjugate base. All right, so this is the Kb expression for this particular base right here. All right, so if we come up those expressions, here's the Ka for this Ha, here's the Kb for this A minus right here. All right, so notice these are what we would have. And what we're going to do is we're going to multiply this Ka times this Kb. All right. And so if we're going to do that, we'll take this expression and multiply it by this expression right here. And you'll notice we have a couple of common terms. All right. So we've got HA in the top over here. We've got HA in the bottom over here. And since these are the exact same HA, all right, we can cancel those out. All right. And this A minus is the exact same A minus as this right here. Those would cancel out. And what we would be left with is H3O plus times OH minus. All right. And hopefully this looks familiar. All right, if you recall, whenever you have this, that is the Kw, all right, which is the dissociation constant for water, which at room temperature is 10 to the minus 14. All right, so what you can say is that the Ka of an acid times the Kb of its conjugate base are going to equal 10 to the minus 14. All right. At room, again, that's going to be at room temperature. If it's away from room temperature, remember it's going to be something slightly different. All right, so technically this has to be at room temperature. And another way that we can say that is we can turn this into a logarithmic scale. We could say that the pKa plus the pKb of its conjugate base is going to equal, the sum of that is going to be 14.